Um, Great. So what I want to talk about is the construction of the coarse Langlands functors. So let me just say a couple legal. Well, let me say what we're going to do, and then I'll put some legal work also. What we're going to do is take the category of D modules. So far, we haven't talked about fungi and we talked about ellipsis, but now let me say what geometric Langlands is. Geometric Langlands is about a connection between fungi and local systems for the Langlands group, and it's sort of what's called the naive. I'm going to do for the theme aside, ellipsis, and briefly reminds that connected reductive groups have what's called the Langlands dual group. This is the reductive group with the dual group data that would be. So what kind of naive geometric Langlands would say is that there's an equivalence between these two categories. So you're supposed to think of this as some kind of space of automorphic forms that has some Hecke symmetries that we'll talk about later in this talk. And you're kind of trying to diagonalize them. And this would be roughly like saying, if there were an equivalence like this, it would be sort of roughly saying that there are, in some sense, one-dimensional eigenspaces, which is a little too good to be true. But what we're going to do is we're going to construct a functor. So that's the main goal for today. Not today, now. For this lecture, just explain how to put this functor. And then let me just say briefly some legal things. So what's going to happen in future talks is that we're going to learn that there's a kind of correction to this category of quasi-coherent sheaves, which is called inco-nilp, which is sort of unwieldy terminology. Like quasi-coherent is already unwieldy. This is more so, but one of its properties is it's going to have a quotient functor. And then what's going to happen in Dennis's talk is there will be an assertion that there exists a unique lift fitting into a commutative diagram like this. With just a couple small properties, making the diagram commutative. And then the eventual goal for the week is the theorem that LG is. So just to sort of organize a little bit what to expect about geometric Langlands conjecture, let me just say these words. So the naive picture would be that D modules on fungi are the same as quasi-coherent sheaves on ellipsis G check, which is a slightly less naive category of quasi-coherent sheaves essentially, but slightly modified with some homological algebra subtleties called inco-nilp, and the same as that D modules on fungi is actually equivalent to this, and that's kind of measuring this failure of the eigenspaces to be exactly one-dimensional. There's some kind of blowing up that happens around certain local systems.
And you said this lift is essentially unique?
It's essentially unique, subject to very minor properties. General, you have to say some category theory words, but essentially unique, yeah. But yeah. Yes, so this is the actual goal for the talk. So now let me just say there's going to be two ingredients. Yep. It's from the off the seed of the red right here. Okay. Then, well, okay, formally this is stuff that's going to come into later talks. It's just sort of preview. but let me just say what's going on. So there's this, and I won't use the right again, but there's this D modulus on bound G. The geometric Langlands says that it's equivalent to encode node on the space of local systems. There are local systems for the Langlands dual group. And what you picture is that in a later talk, there's going to be a construction of the functor that compares the two. Saying how you get from A to B. The rest of the week, so that'll happen later today. The rest of the week is going to be about the assertion that that functor is an equivalence. And what we're going to do today or what we're going to do right now is to do what's written, which is instead of going to this slightly fancier category, slightly more subtle category, we'll go to this category plus differentiates and such.
So there's one question, I guess, the definition straight. In general, D modules means multi-differentiates on the ground stack.
Yep.
And this is literally just the ground stack of 1G multi-differentiates on it.
Yeah. Okay, so there are two ingredients in the construction. So the first ingredient is the existence of a certain compact object. So I think it's called like this. Some D module by G. It's impact, which I'll say that means when we talk about it. And this is called the Poincare sheaf, or the vacuum Poincare sheaf. And the second ingredient is the spectral action. Which is a canonical action of the category of flexible coherent sheaves on locus G check on the category of D modules on G. And let me just briefly say that this is related to the Hecke action. As we'll see later in the talk. So, but this is clearly kind of a major thing. Like, look, here's one side of geometric Langlands, essentially. Here's the other side of geometric Langlands. And so there's it's not crazy that this is going to play an important role in comparing the two things. And this is, let me just say right now, this is going to be what most of the talk is about. But let's just black box those two things for a second. And I'm going to then explain what it comes to do. Okay, so before doing that, let me just say one word about this this compactness. So what this means is that the functor maps out of this Poincare object. So this is by definition going to be something that we call the basic Whittaker coefficient. The statement that this is compact means that this commutes with direct sums. With infinite direct sums. Which is the same thing as saying with all colimits. So I'm just going to mention those words briefly, and we'll see from the construction that that's kind of an evident property of this. Okay, so now I want to say so kind of in order to explain the construction of the functor, I need to say briefly sort of a slight variant on Unitas lemma for flexible coherent sheaves. And here y has to be an algebraic stack with some properties. Various things are going to be needed, but I'll mention what they are. Especially when asked. So if you're given a quasi-coherent sheaf, then this gives rise to a functor f sub p from quasi-co of y to the category of vector spaces, which sends a sheaf H to the global sections of y with coefficients in the G tensor H. And this functor commutes with colimits. So this is part of my assumption from y. I'll just say that now. And then there's a claim, which is that the induced functor from quasi-co of y to a category of functors that meet with colimits, which is sometimes called continuous, from quasi-co of y with that this is an equivalence. So there's K linear functors. And let me just briefly say my assumptions. So so y should be quasi-compact. So like ellipses, it should be should have affine diagonal, and need a very mild condition like the quasi-co of y is dualizable. There's okay in the by family component category, which also we don't really need here. But I'm just saying there's some technical hypotheses on y, very, very mild, absolutely true for ellipsis. As Seema explained. And what this does is this tells me, so this is a version of the Oneda's lemma. It says it's not like comes out of an object here, it's sort of like you tensor with the object and do global sections. So it's a slightly kind of dual version of
So
yeah.
this so it uses a notion of a rigid category. Which,
Yeah.
In particular, implies this, and I was wondering if your theorem is that it's a rigid category.
Yeah, exactly. It's a rigid category in that sense. That's exactly right under these assumptions. So like in principle, you can be a little bit anxious about y quasi-co of like y times y is quasi-co of y times of quasi-co of y. That's the kind of issue you run into. You need this kind of thing. Quasi-compactness of that one diagonal. The structure sheet is compact.
Also, is it not that it's dualized version on the it's the inductor, so it's not with.
It's not known. I think that there, as far as I'm aware, there's no general theorem. This might just be my ignorance, but like in characteristic 0, I don't think it's known any examples of quasi-co of some kind of reasonable stack, like quasi-compact and affine diagonal, which isn't compactly generated. But there, so the only cases where people can prove that are kind of under restrictive hypotheses. It's known that if the structure sheaf of y is bounded, if y is eventually co-connective, then quasi-co of y is dualizable. So that's what Trent-Folding gets very proved. But it's not known whether it's always compactly generated.
Yeah, absolutely. Yeah, but if this forward not demanding itself to
It will automatically be self-dual. That's what it kills. That was the first of the kills. What I did is really I wrote down a pairing between quasi-co of y and itself into vect, and I'm saying that that's a self-duality. Other questions? Okay, so the so now let me just say sort of, so what I'll do is to define LG LG coarse is F for F not divided by G. I'll use this dual nonata. So what I'm going to do is I'm going to write so for every G in quasi-coevoxis you check, then by definition, okay, what I need to tell you is global sections of Voxis to check with coefficients in G tensor with LG coarse of this F. And by definition, I'm going to apply this Whittaker coefficient functor, this thing that's sort of equivalent by honest unita to functor G. And I'm going to do G star F. So this is the special action. We'll just go right here for a second. So okay, in purple, it's not so visible, right? How about blue? Yeah, that's more visible on the back, but okay, the blue. So let me just say one of the basic axioms of geometric Langlands. So one of the basic axioms of geometric Langlands is that this functor A sheet is supposed to map to the structure sheet at locus G check. I haven't told you what the functor A sheet is yet, but I sort of want to highlight this. And what you can see is that we've kind of rigged this. So the definition of LG coarse is forced by this construction, by this requirement.
When you say active, you mean the things you want your function to satisfy.
Okay, so what I mean is the following. So I told you two things. So there's the spectral action, and I told you an object. Like, I'm saying if you want to have something which, like, let's forget fancy things for a second. Let's say you wanted an equivalence, which sends the functor A sheet here to the structure sheet here. Then you wanted it to be an equivariant for the action of quasi-coevoxis, then it has to be the functor A sheet. So I said some kind of abstract words, I made this one, blah blah blah. I'm just trying to say that it's forced by this requirement. So maybe let me write it out.
What's the tensor product taken over in the upper line?
Oh. Yeah. Just exactly as over that. So maybe let me just say the basic proposition here, which is that LG coarse is the unique quasi-co of Voxis G check linear functor such that the following diagram commutes. So that we do mod of 1G. Here I take LG coarse. Here I take this coefficient functor, just how out of this functor A sheaf. Here I take the global sections functor, which is Ham out of O. And so if you wanted the Poincare sheaf to map to O, this diagram is better complete. And, you know, to believe in truth, justice, and the American way, then it should be quasi-closed looks as T-type linear. Okay, questions about that? Yeah.
How do you do this confirmation?
I'll tell you what it is. Yeah, so I have two conditions here, but
So you say it's me.
I'll tell you that I'll say this is it. It's like, am I unique?
From what you said, I thought you would somehow put in a confirmation and you get out of the Langlands from that. So here.
No, there's one. Yeah, there's a single one. So what's the logic of the talk so far is here are two things I haven't told you, but will tell you in the course of the talk. And if you believe me that I've already told them to you, then I did the other parts of the talk, which you might not have. So it's I sort of want to say, I promise two things, I'll fulfill both promises. Yeah. Okay. That make sense? No. That's a. Other questions? Okay, so first let me do this Poincare sheaf. So let me take I think the notation wasn't given yet, so this is going to be the Borel, which maps to the Rakan, and n is equal to the kernel of this map, so the unipotent radical of B. So if you think a little bit, then bun n is equal to the fiber product of bun B times over bun T with the trivial bundle. So it's an n bundle is just the same thing as a B bundle whose induced T bundle has been trivialized. And let me just give a quick feeling for these things. So as a quick example, if G is equal to SL2, so B is equal to the subgroup A inverse B, and it's 1 B. B is equal to GM, so the matrices in this form. And just to give you a feeling of how to think concretely about these things, so bun B is going to be the set of extensions which is supposed to be like, here's your A inverse, and then there's this sort of extension that this B represents, and that's this extension. Bun T is just bun GM, it's this moduli space of line bundles, and then bun N is the set of extensions like this. The set that of course it's exact. So what I need to talk about is not really bun N in order to define this Poincare sheaf, but the variance I'll write like this, bun N omega, and this is by definition the fiber product of bun B over bun T, not with the trivial bundle, but with the bundle rho of omega x. So here 2 rho is equal to the sum of the positive co-roots. So one of the things I did, so when you start doing, like, if you wake up and say, I want to work on geometric Langlands today, there's a few things you should fix. So you should fix a reductive group, you should fix a curve, and you should also choose a choice of square root of the canonical bundle on that curve. The good news is it always exists, so that's another great exercise. And there's finally many choices of isomorphism. And then rho of omega x is by definition 2 rho, which is an actual co-weight applied to omega x to the 1/2. So brief comment. So can't take a feeling, so for G equals SL2, this finite omega is going to be the modular space of extension to the following form. Really dangerous territory here. Which you can kind of think of as something like R gamma of omega x, well, of x, kind of thought of as a stack and with a shift by 1. So if you're happy to think of like a finite dimensional vector space as a scheme, you can think of a complex in degrees -1 and 0 as a stack. And then by design, again, if you think really hard about chain complexes, this maps to H1 of x with coefficients in omega x. And the reason I like this twist is that this is A1. So
So in this expression, where are like what's this? This A1 is H1?
okay, I can put an underline here also. The underline means like take this vector space and think of it as a. If you take a vector space, you can think of it as like a scheme. Let's say finite dimensional vector space.
The question was, recall third duality, but each one of omega is A1.
Yeah, this is their duality. Sorry. Was it?
I formally don't understand the expression because like there's an equal sign, there's an arrow.
So what I'm saying is the following. So if you take like literally the vector space H1 of x with coefficients in omega x, then their duality identifies that with K. Like the one dimensional.
Okay, so the first thing in the last line is just one and omega.
This is just one and omega, exactly. Yeah.
Maps to A1.
And I'm saying it maps to A1.
Okay, thanks.
And yeah, and like the way this complex looks, if you're like allowed to split complexes, it's a little bit non-canonically like B of H0 of omega times H1 of omega. So there's some kind of like stupid stacky part here, and then there's like an A1 basically. And so yeah. So
Rho of omega x is a T bundle on.
yes, this is a map from GM to the torus, to co-weight. And so if you hand me a GM bundle, aka a line bundle, then I can induce it off to be a T bundle. Yeah. Which in practice looks like you take this omega 1/2 and you put the half here and the minus half here. So that was like an A and that was an A inverse. So for general G, for each simple root gives rise to a map from N into GA, and therefore it gives rise to a map from fun N with this omega twist to sort of fun GA with an omega twist. Again, it's this R gamma of x coefficients in omega, which then maps to A1. So these glue together to give me a map from bun N with this omega twist into an affine space to the dimension, the semi-simple ring of G, which then I can map to A1 by summing the coordinates. And I'm going to call this resulting map psi. So this is this idea of working with a reductive group. So yeah, so you should kind of think of, again, maybe for like GL3, kind of imagining like my group is sort of like this. I don't know if this will make sense to anyone, but I have some twisted version of N. So it's a group scheme over X. And the sections, the points of N look like a section of omega, a section of omega, and a section of omega squared. Instead of, like, the twist is that otherwise I would have sort of functions here. And so I can talk about bundles for this group scheme, and that's what I'm doing. And now, so it's kind of H1 with coefficients in this group. And then what I'm doing is I'm summing the classes along, above the diagonal, kind of along the nodes of the diagram. And that sort of construction goes by the name like Whittaker block. So the name Whittaker gets attached to this idea of summing over the nodes of the Dinkin diagram some kind of non-trivial characters. Okay, so now what is this? This is Poincare sheaf. So by definition, this is going to be. I'll write the formula and then explain what the terms mean. Where Pn is the map from this bun and omega into the bun G. So like in this sort of picture, I'm just like, it's like I take this extension and I just extract E as an SL2. So this is the projection, or another way to say that is just very formally, the spun and omega was defined so it maps to bun B. The B bundle is an extra structure, and the B bundle definitely induces this D bundle. And then this exponential sheaf is going to be OA1 equipped with the connection nabla equals 3 minus dt, which is a D module on A1. And so what's happening, like why do I call this X? It's just if you think about the function e to the x, or e to the t, I should say, it doesn't make sense as an object of algebraic geometry because it's a power series, not a polynomial, or it's a holomorphic function, not a polynomial. But it does satisfy an algebraic differential equation. So if you don't know how to sum an infinite series or something, then you still can understand the statement that you have some function whose derivative is equal to itself. And that's what's encoded by this connection. In the usual dictionary between connections and ODEs. And so that's what I'm doing. I'm just writing down the differential equation for the exponential function. And then I'm pulling it back to the star and omega and pushing forward along this map. This is the usual lower group module operation. And let me just say that this functor of coefficients of some object f, if you think about what it is, this is going to be computed by just taking. Yeah, let's see the ROM to be very official about it. What that means. So this is fun and omega, and then what I'm going to do is I'm going to take my my sheaf graph, I'll pull it back, still on n, and then I'm going to tensor do that. But this is what this. Oh, and this is this just means surround homology, but I want to emphasize that I think of it as a chain complex and not as a graded vector space, not actually the complex itself. Yeah. So that's what the Poincare sheaf is. So it's a particular sheaf. Let me just make a. There's one very trivial example. So, as an example, so if G is equal to Gm, then this functor A sheaf is going to be what's called, so it's going to be the skyscraper sheaf, and I'm going to put a little streak here, P modules on bun Gm. And what does that mean? So there's a map from the point into bun Gm, which is given by the trivial bundle. Usually points are closed and things, but as Justin explained in his talk, points are not, well, okay. So the fibers here look like GMs. So there's something a little bit non-trivial about this map, a little bit less trivial than usually putting a point in. But then what I do is I just streak push forward the constant sheaf. And so this is just some version of a skyscraper sheaf sitting at the trivial bundle. And for stacky reasons, you have to think a little bit. There's two kinds of skyscraper sheaves, and I'm telling you which one it is. Now, what you're supposed to imagine is happening is that this is the sort of Dirac delta in the case of GM, and in usual Fourier theory, Dirac delta at the origin corresponds to like the function 1. So this is the thing that under sort of geometric Langlands for the torus is going to go to O, like it was supposed to. And then there's I think if you've never seen this stuff before, there's a quite non-trivial assertion, which is that kind of Whittaker sort of constructions are the kind of correct non-abelian analog of the Dirac delta at 1. So this functor A sheaf, you're supposed to think of it as a kind of non-abelian analog of Dirac delta at the origin in abelian Fourier theory. At least, if you buy into the philosophy, that's what's happening. Okay, so that was the first 5 minutes. At 20 minutes, I end at 12:30, yeah. Great. Okay. Any questions? I told you who the functor A sheaf is. It's a particular guy, yeah. Say again?
What's the left underneath that arrow from the point?
Oh, it's saying that the fibers of this map are GM. So it's like, yeah. Yeah.
You told me for GM in terms of GM.
Yes.
Okay.
So if you want a concrete description, okay, there's stuff you can say. If the genus is at least 2, and blah, blah, blah. I think we'll say it later in the right? Yeah. It's a pretty fun concrete thing. At least
It also has very small support.
I don't know what support is, because like points aren't closed, so kind of just support okay. For non-abelian groups, there are no closed points inside of bun G, and so like in some sense your support can't really be closed. But like this finite omega is quasi-compact, so like it is extended from some but quasi-compact by this one. So it's very 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 binary.
Well, this analogy doesn't function. So you're saying that you cannot talk about support for it.
Yeah.
Hmm.
Yeah. But yeah, it's kind of, like what you sort of imagine is it's more like naively you might have thought that like you would look at the skyscraper sheaf of the trivial bundle, but the statement is it's not really the skyscraper sheaf of the trivial bundle, but it's more like the bundle of rho over omega in the first place. Okay, but then it's not really even like the skyscraper sheaf there, it's some kind of something more hyperlocal.
You can also try plugging in E1 into the formula and ask where this sheaf will live on the picture of bun of bun T1. And that's the question about extending of 1 divided by of -1.
Yes.
Maybe I would answer, but like, in the classical Langlands, one specific non-general factor with n. You look at the induction, so what's the reason for twisting to?
Okay. The reason for twisting is that in that story, you choose some character of like n of DLs. Yeah, which is supposed to be trivial on n of f at the end of the global field. And it's kind of a, you know, sometimes maybe there's a preferred way of doing this. Well, in the case of curves, that kind of depends on the choice of like meromorphic one form, the generic point of the curve. But that's always, if you think about it, you can never do that in a way that's going to be sort of unramified everywhere on the curve. If you have a one form on the curve, it automatically has some zeros. There are many choices of one forms, but they'll have zeros, and so you can't do it in a way that kind of feels correct. And so what you do instead is you kind of do this twisting, which is like extremely mild. You can't see it. Like in other words, what this does is it absorbs that choice of one form. So I didn't have to choose the one form in order to do the character. It was completely canonical. But of course, once I choose the one form, like generically, then when I sort of puncture at that point, this group scheme becomes the trivial. When I puncture away from the zeros of the one form, then this group scheme becomes isomorphic to usual n. So it's kind of like you should think that in number theory, people very rarely talk about everywhere unramified automorphic forms on curves, and so we don't really kind of run into this sort of kind of situation.
Right, you said that last sentence again.
Yeah, in number theory, people do not like usually they talk about number fields, and number fields don't really have a notion of everywhere unramified automorphic forms. Yeah, which is kind of what we're doing here. When we deal with this proper curve, there's sort of no puncture. So what happens in number theory is often a punctured kind of situation. They might think about the field of meromorphic functions more than like sort of the generic point of the curve more than the curve itself. And so there are certain so if you think hard about the unramified situation, you realize that this twist is very convenient. More natural normalization. What's written here? Oh, constant. I mean, yeah, just it's like a point. There's like one reasonable. Don't push forward zero. Don't push forward like the two-dimensional vector space. Yeah. Other questions? Yes, that was yeah. I said it as an exercise, so yeah. Nice exercise. It always exists. Yeah. Other questions? Okay. So so now let me just sort of briefly say something about the Hecke action and the spectral action. So if you fix a point in the curve, then Justin said that there's this sort of Hecke groupoid acting on Bungie. And then geometric Sataki, into Lustig and Grinfeld and Mirkovich and Volonin, constructs canonically a functor from rep G check into this category of D modules on the Hecke stack. How is it written, Justin?
So G on S.
And let me just say very briefly how this works. So fortunately, we're in characteristic zero, so this is just some semi-simple category. There's some highest weight theories. And this representation V lambda is going to map to the IC sheaf on some orbit. Maybe with a shift. So again, just some kind of very explicit construction. And so the upshot Is that whenever you have a representation of each f and this closest point on the curve, there's something called the Hecke functor attached to this data. The corresponding Hecke functor, which is given by you pull back to the Hecke stack tensor with the Satake sheaf, and then push forward with it.
Sam, so was Justin told, I guess that, but don't over that.
Okay, yeah, I was kind of forgetting. I was trying to avoid whether
It's like heck of a balance product.
If you want to write it down, yeah.
the goal there.
Well, Justin also said that we have. Yes.
Yeah. Okay, I'll say. So so here's the setup. So there's this Hecke GX global, which is going to be by definition the set of pairs of bundles plus an isomorphism between the restrictions to a punctured curve. So so this has the following sort of structures. So it has two evident maps to Bun-G, which are traditionally written H left and H right, but this is just like, let's say this is like the map PG, and this is the map like PG tilde, extracting this data, and then there's a map to this local Hecke stack, which is the set of pairs on the disk. Representation on the disk at X with alpha defined on the function disk. And so your Satake sheaf. So what you do is you so what you should imagine you're doing is you're taking a sheaf on Bun-G, you're pulling it back, well, and then you're trying to produce another sheaf on Bun-G out of that. And what are you going to do? So you're going to sort of count the values of your sheaf on Bun-G along all possible modifications of G at a point. So you look at this, so you start with a sheaf, which is something which sort of takes bundles and produces vector spaces. And then you want to get a vector space out of some other bundle. And what we'll do is like that other bundle lives in this copy of Bun-G, so to say. And so what you do is you count all the possible modifications. You take the fiber of your sheaf at the first point at this key G, but then you weight that according to some kind of measure. That measure is just pulled back from the type of the local modification, what's happening just near the point. And the specific measure you're supposed to take in this business is the one coming from this Satake sheaf. So there's a variant on this. So basically, what if I need many variants on this construction. So the first variant is I don't fix X. And so then what I'll get instead is that if I fix a representation, then I'll get a functor, which I'll just call HB from T modules on Bun-G two modules on bungee times x. And what its job is that if you take the fiber at some points, so let's say this is like if you can put well, this is going to be my HDX. So it's some way of encoding all of the Hecke functors as you allow points to vary. So it's going to look exactly the same as the construction here, but I'm just going to allow x to be a variable point now. Um, so that's the first variant entity. Any questions? The second variant is that I might fix two representations, or I might take a collection of representations indexed by some finite set. And then what I'll do is I'll compose HV with HW for all of the VIs. So now this gives me a functor from P modules on bungee to P modules on bungee times x squared. And there are some relations that come from the geometry of geometric topology. And these say the following. So HV composed with HW is equal to HW composed with HV composed with the swap map along this x squared. So in other words, if you give me two representations, I could have done HV and then HW to get here, or I could have done HW and then HV to get here also. And those are just going to be completely the same functor up to the fact that sort of you ordered the points differently. They should swap it over. Also, if you restrict along the diagonal map, then you obtain H of V tensor W. So if you restrict either of the functors, and then this is also compatible with the commutativity. So what do I mean that this is compatible? I mean there's some kind of, if you take this isomorphism and you restrict it along the diagonal, then you get sort of the obvious isomorphism between V tensor W and W tensor V. And so I guess variant 3, which I was hoping to say more about, but I guess I won't, is that this category G check on acts on the mod of G. And if you think what an object here is, it's kind of a picture that follows. So this is kind of, in other words, the most basic objects of this rect G check run look as follows. They're sort of little points, and then at each one you attach a representation. And a picture like this, yes, all of these elements of rect G check. And each such picture gives rise to an object of this rect G check on. And my action is going to be such that this is gonna act by this H. This is why I shouldn't use X, Y, Z, but it's going to act by H V X X composed with H V Y Y composed with H V Z Z. So it's just the composition of Hecke functor. So that's how this is written. And if you just sort of think out like really what these combinatorics are saying, especially in the setting with these sets I, then and you start this rep check run a little bit, then you can really obtain this assertion. Questions?
What do you choose the ordering there for the composition?
That's the thing. I think what's said over here is the ordering doesn't matter.
And that's okay.
Yeah.
Actually, and it just to not mislead people, it's not that you, this is like a nice way of saying it, but like. This is something you can kind of extract by just drawing this entire convolution diagram and the whole thing taking place overall. Right, it's also encoded by the convolution diagram, this action. This is kind of like a discussing what it's about. Like a logical.
That's not included.
I mean, modular proving dynamics.
Well, no, I mean I'm sort of really using the commutativity constraint. Yeah.
D Y H G X as I allow X to variable on X on this, and is it part of Geometric Switch that thing that I can naturally make over on X and rep G check Ron are the same thing? Battle all that structure.
So okay, you have to be a little bit careful. So okay, one of the secret things no one said is all categories are derived here. So yeah. But geometric Satake is not true as an equivalence of derived categories. So you see equivariant cohomology come up when we compute X in the Satake category. And so it's not true that it's on the nose equal to rect G check. Up to that issue, yes, then this quasi-correct G check run is somehow the naive version, so to say, that the category of modules on the set. Yeah. But it's to say that's not a formal consequence of the usual statement of geometric Satake. You have to stare a little bit at the commutativity constraints.
And that's the little sense of then the geometry of.
Yeah, exactly. That's where that's exactly what the vague statement meant. That's correct. Other questions? Okay, so now I promised the spectral action, and so the statement's the following. Okay, I'm gonna write one more illegal word, just like I have this conscience. No one else is worried about it, but I really need. Okay, so the statement is that there's a canonical functor, canonical symmetric monoidal functor, which is often written log spec, and this is the evaluation bundles.
What did you write in red?
Let's leave it for the question session.
We can't read it though.
I know you're not supposed to. Okay, so there's the functor, which is what Dima was calling the construction of evaluation bundles from rep G check run into this quasi-colloc sys G check, and I'll call this spectral localization. And so roughly speaking, the idea is that if you have a point in a Ron space, this is going to give rise to a map from log sys G check to sort of this. I forget what Dima called it. BG check Ron. Is that what you called it, Dima? Where is Dima?
Yeah, well, it was
Point my G check. So you'll get a map from this log sys G check to this point G check run. In fact, sort of the fiber of it at this given point X. So it's to say, like, if you choose 3 points in your curve, you're gonna get a map like this. You're gonna get a map from both sets G check to like point mod G check times point mod G check times point mod G check, which is just restricting your boundary to the formal neighborhoods to like those 3 points. And then you just pull back. So look stack is pull back elements. And so there's a theorem due to Ginsberg and Rosenblum. Which is very difficult to track down. It was sort of folklore for a long time, but it says that this Bloch spec is a quotient functor. And let me emphasize maybe that it's symmetric monoidal by design. And so finally got written down in GLC4, which is sort of very psychologically out of order, but there's still sometimes and I don't have the precise reference here, but it's really the introduction of the and then there's a theorem of Drinfeld and Batesbury. Which says that there exists an action that the action of rep G check run on two modules on fun G factors through an action Q total of looks as G check. Which is a property, not a structure. It's a property because this is a quotient functor. So this means that if you have some object, like script B, in the kernel of this Bloch spec, it acts by 0 on G module on fun G. You were hoping to. Okay. And this theorem is also difficult to track down. So Dennis wrote a short note about it. It also occurs, so this is called generalized vanishing conjecture. There's both Dennis has a paper with this title, and it also occurs in his outline of the proof of geometric Langlands for GL2 paper that Dima referenced earlier. The argument's written sort of twice. In both cases, it uses various facts that weren't written at the time, and the proofs were written later in GLC2, and will be discussed also later in the week. So I would say the refs are this plus some input from GLC2 and this aforementioned GLC4. Write it down. So, okay, I'm a little over time, but worse than I thought. Okay. Sorry about that. Yeah.
Let me add that in my talk, I'll recap a little bit of what both Sam and Gina said. But if you missed some parts of it, don't worry. It will be reviewed again today.